Hi, everyone. I'm Amy McDougall, and I am here today with Dr. Zachary Grasley for Open Air to help everyone understand how they can lower carbon in concrete, which is such an important building material. So let me introduce Zach. He is the director at the Center for Infrastructure Renewal. He's also a professor of civil and environmental engineering and a professor of material sciences and engineering, all at Texas A&M. They're lucky to have him. He's also chairs the Material Science of Concrete Committee at the American Concrete Institute, or better known as ACI. He does a lot of research around cement-based materials and is active not only in the ACI, but also in the American Ceramic Society. So Zach doesn't have much free time. So Zach, welcome. Thanks for taking some time out.
My pleasure, and you forgot to mention all-around nice guy.
Oh yes, an all-around nice guy. The most important thing, I should have led with that, but I'm sure they can see that from your all-around nice face. Let me just jump right in. So why is this such a big deal to lower CO2 from concrete, and why does concrete create so much CO2?
Sure, yeah, I think most of the population has gotten a feel that concrete is a large CO2 producer, that the production of concrete is a large CO2 producer. There's lots of articles out there in news and websites. There was a headline sometime back, concrete, the most destructive material on earth. But there are a lot of subtleties to that I think it's worth pointing out. A lot of people don't realize that the main reason that concrete production results in so much CO2 is simply because of how much we use. Not because concrete in and of itself is a particularly bad material with respect to CO2 emissions. In fact, if you compare concrete to alternative materials like steel or aluminum or any other materials you might choose instead of concrete, concrete stacks up very good on a per structural capacity basis in both energy consumption and CO2 production. And so the fact is, we just use a lot of concrete. Concrete's the most widely consumed manufactured material in the world by far. No other materials are even close. And so, this is a good thing and a bad thing. The bad thing is that you're getting all this CO2 production. About 4 to 8% of global CO2 emissions comes from concrete. But you can also look at it as an opportunity, meaning if we make some even small improvements to concrete and reducing its CO2 emissions on a per mass basis or per cubic yard basis, it adds up. It'll have a huge global impact.
That's great. So I get it. The cement really drives a lot of the CO2 around concrete. We use a lot of concrete because of all of the great properties of concrete that you mentioned. But, I've heard a lot about people substituting things for cement or trying to come up with cement alternatives. Do we have to use cement to make concrete?
Yeah, if you didn't have cement, you just have muddy water, okay, with a little bit of sand and gravel, crushed rock mixed in. Cement is the magic powder. Cement chemically reacts with water to form these different solid products. Calcium silicate hydrate is the main one, that essentially glues together all of the sand and the rock to make a hardened mass that has the properties of interest to us as engineers, right? It gives us the strength, the durability, the thermal properties. All of these characteristics we need depend on there being cement, this chemical reaction between cement and water. So you can't totally get rid of the cement.
Great. Well, are there ways that we can reduce the amount of cement or use in addition to cement?
Yeah, there are a lot of efforts out there, number one, to try and come up with new materials to replace Portland cement, so other kinds of cement that also will have a chemical reaction to kind of glue the rocks together. But there are some limitations there. Earth's crust is made up, 99% of Earth's crust is made up of about 8 elements. And so our palette of potential materials is pretty limited, okay? Furthermore, this development of these new materials has to be seen as very much a long-term solution, right? I'm talking 10 plus years out, maybe 15, 20, 30 years out. In part because of how much cement we consume currently, how big the market is you'd have to try and displace. And also if there's different manufacturing processes, trying to actually build up the capacity to do that. And then that's not even considering the fact that we would have to create new codes, building standards, potentially equipment to utilize this new material, and so on. So that's a long-term solution. In the near term, though, we can certainly replace portions of the cement in our concrete with other mineral powders. And in many cases, we can actually get improved concrete performance, right? So this is one of the few cases in engineering where you can have your cake and eat it too. Usually there's trade-offs in engineering. In this case, you can actually improve your concrete while reducing your cement content. And so some of these mineral powders you can use are actually waste products from other industries, like fly ash, which is a waste product from coal burning power plants, granulated blast furnace slag, which comes from the production of iron and steel products. And these things will actually allow you to replace a portion of the cement with these waste products from other industries, and therefore lower the overall CO2 impact of your concrete.
Great. And there's also, I believe, you hear a lot about people using liquefied CO2.
Yeah,
talk a little bit about that.
This technology is a bit of a newcomer to the industry. The replacement of a partial replacement of cement by mineral powders goes back decades. We've been doing that for quite a while. Maybe not in the most efficient way or in the most optimized way to reduce CO2, but we've certainly been using those materials for a long time. CO2 dosing of your concrete is pretty new, and a company called Carbon Cure has helped lead the way in developing that technology. And the concept is that you inject a small amount of CO2 into the concrete. So you're not really using up a lot of CO2 in that part of the process. However, the injection of the CO2 will essentially provide precipitation of these little tiny particles inside of your fresh concrete that provide seeding sites for the calcium silicate hydrate, that the main glue that holds concrete together, to grow on. And so that allows you to get more rapid strength gain and allows you to actually cut back a little bit on your cement content. So it's just another means to reduce cement content and therefore reduce overall CO2 footprint of your concrete by reducing that component of your concrete that results in the most cement CO2 production.
Great. And so when you think about, there's a lot of different producers out there who make ready mix concrete. Well, we'll talk more about ready mix concrete, not so much precast concrete for this discussion. But when you look at all of those suppliers, is there any reason why they wouldn't all be rushing to use all of these different materials and, lower the amount of cement that they currently use today with slag or fly ash or liquefied CO2? What's stopping them?
Yeah, so there's certainly an economic incentive in many cases to replace cement, because cement is still often more expensive than some of these other mineral powders. And so most producers would certainly like to increase the amounts of these things that they use, strictly from an economics perspective, even disregarding the environmental impacts. However, most specifications for construction projects in the United States are either prescriptive, wholly prescriptive, or more often a mixture of performance and prescriptive, whereby the producers are given certain performance specs like compressive strength at 28 days or at 3 days or whatever. But then they're also given restrictions and constraints on exactly what their mixture design looks like. So, one of the complaints that you'll hear from producers sometimes is that they're told what their cake has to taste like, and they're also told how they have to make their cake. So, this type of prescriptive specification might have an upper bound, for instance, on the amount of fly ash or slag that you can include in your concrete. And those upper bounds are probably overly conservative in many cases. And, if they didn't exist, then producers would have an incentive to try and optimize their mix designs to increase those things, particularly if there's incentives surrounding CO2 reduction.
Great. So some of those incentives could be in the form of legislation, correct?
Sure.
Yep. I know we've been hearing about different laws that are either passed or being passed in different cities, states, where they're really encouraging more, lower embodied carbon concrete. So that might be another incentive to get people to do it more often and to push back on some of the customers that are ordering concrete that is prescriptive instead of performance-based. So really good points that you made. So we've talked a lot about cement and alternative materials, but what are some of the other ways we can lower CO2 creation from concrete, considering this is quite an arduous process, right? From, creating the raw materials, getting them to the plants where they're producing them, and then delivering them. Can you touch on any other areas that could help us lower CO2?
Sure. Well, I mentioned that the cement itself, the production of the cement itself, is the main contributor. You get about 9/10 of a pound of CO2 produced for every pound of cement that you produce. But certainly it's not the only place where CO2 is produced in the manufacturing process, cradle-to-grave manufacturing process of Portland cement concrete, right? So by the time you get that concrete to the job site in the forms, there's a few other places. The other primary place where CO2 is contributed is all of the transportation. Concrete is a very dense material, right? It has a very high unit weight, 150 pounds per cubic foot. All of the raw ingredients that we transport, the rocks, the sand, the cement itself, all have very high specific gravities or densities. And as a result, there's not only large transportation expenses, potentially up to half the cost of the concrete itself could be wrapped up in transportation costs. But there's also large environmental costs as a result of that too. There's a lot of CO2 produced in hauling around this heavy material. This includes, transportation of the cement to the batch plants, transportation of sand to the batch plants, aggregates to the batch plant. And then once the concrete's produced, you've got to transport that to the job site. And, often a lot of the major concrete construction projects that consume a lot of concrete are in urban areas where people don't like batch plants to be sitting on this expensive, valuable land in these densely populated urban areas. And so the trucking is often reasonably far. Or you've got, large LNG facilities being built on the Gulf Coast that are a long ways from any kind of a producer. So transportation can be very significant, particularly as we, continue to refine our concrete mixture designs and reduce the amount of cement in there. And if we are able to, through legislation or whatever, to get more incentive and reduce some of these restrictions in these prescriptive specifications that allow us to optimize on the cement content. After that, what you're really left with to optimize is the transportation in order to optimize the amount of CO2 you produce.
So it makes a big deal if you're someone sourcing concrete and you see plant A is 20 miles away and plant B is 5 miles away, and the price is the same and the mix is the same as far as they've lowered as much cement content as they can. If you want to do the right thing for the planet, you would go with the plant B that's closer to the project. It sounds like it would lower a lot of miles on the road as well as potentially number of trucks, because you have a closer time span to kind of distance out how often you need it, and you wouldn't have as much waste maybe at the end of the day, things like that.
Sure. Yeah.
Great. And really good point.
Yeah. And, as you optimize the cement content, reduce the cement content within concrete, for typical transportation distances, the CO2 contributed from the transportation process of getting the concrete made and then also delivered to the job site could surpass 25% of the total CO2 production. So it's certainly significant. And then you also highlight another subtlety that I think is easy to overlook. This is a very complex problem, the CO2 production, and trying to minimize it. In part because there's all of these unseen factors that never get considered, right? Transportation is often overlooked when it shouldn't be in the production of concrete, because people simply accept that, oh, well, we got to get the materials from point A to point B. And, it'll just get improved as vehicle emissions get improved. But also you mentioned the miles on the roads, right? And so if you have damage occurring to roadways, and almost all damage, on roadways occurs because of heavy trucks. Cars essentially do zero damage to roadways. That roadway then has to be replaced, which means you're producing new material then to replace or refurbish that roadways. These are kind of these subtleties that are often hard to quantify in these problems.
Right. More collateral damage, as they would say, from the choices that people make. Yeah, that's great. Excellent point. So beyond that, what are there any other things? I know concrete consumes a lot of water too. We've talked about sand, rock. I think there's even different types of rock that you can choose that can lower your cement. I don't know if you want to touch on that. And then the amount of water that we use to not only create the concrete to make the mix, but I know we need a lot of concrete to wash down the plants and the trucks. And if you want to touch on any of those areas of ways that people can consider what's happening there to lower CO2.
Yeah, I mean, with respect to the choice of aggregates and so on, certain types of aggregates will allow you to reduce your cement content and maintain things like workability and so on. But that's down in third, fourth order effects, I would say, in comparison to the transportation issue with the aggregates. You wouldn't want to choose an aggregate that you have to transport a lot further, and truck a lot further just because it lets you reduce your cement content a tiny bit. With respect to the water issue, you mentioned the wash water, and certainly, that is another area that I think, people are starting to think about, at least, people in the research community are starting to think about, and maybe some producers as well. When you make concrete, cement raises the pH of the pore water, the mixed water that you make your concrete out of, raises the pH up to about 13 or 14. Extremely basic or alkaline material, and this if you've ever made concrete with your bare hands, and it's kind of peeling your skin off afterwards, right? So that's concrete. The problem with that is that if you wash out a concrete mixer drum, or you wash out a pump, or a drop pipe, or any other equipment that's been in contact with that concrete, that water now has dissolved cement ions in it, and it has a very high pH. Maybe not as high as 13 or 14, but certainly higher than you'd want to be just releasing directly into the environment, or to reuse to make more concrete, or repurpose for almost any use. And CO2 is a great material for actually neutralizing high pH liquids. So you can inject CO2 or bubble CO2 through high pH water, like concrete wash water, and bring its pH back to a neutral level, so that water then can be recycled and repurposed and reused in a safe way. Just one more.
Great. No, those are really good points.
Again, it's maybe not a huge on a per cubic yard basis, but we use so much concrete that if you started doing this on a regular basis, it all adds up. Plus, Plus, you're not putting this highly alkaline material directly into the environment, which can cause other kinds of environmental issues.
Yeah, that's great. So, I've heard a lot about and understand, and we're even at OSL working on some EPDs for our plant. We manufacture and pump concrete from a ship. So our ship, number one, removes a lot of trucks from the roads, but we are able to do exactly what you described with our wastewater. We can inject liquid CO2 into our wastewater and reuse it, so we recycle our water. And so we're able to take advantage of a lot of those things that you just mentioned, and so I'm feeling pretty good about it. But if we're just kind of someone who's maybe not in the industry, or maybe they haven't thought, maybe they're a producer and they haven't thought about doing EPDs yet, environmental product declarations is what EPD stands for, just to slow it down for a second. How do people make sense of this? Or do you have any comments on that? And if not, I can talk a little bit about a new tool that they introduced where they are housing a lot of these EPDs if people want to kind of get a leg up and understand them a little bit better.
Yeah, so I mentioned earlier that this is a complex problem, and because of its complexity, there's got to be some sort of a standardized way for people to compare, one mix design versus another, or one concrete from one producer to concrete from another producer delivered to the job site. What is the environmental impact of that? Similar to adding up the dollar cost of something, right? And here we're just adding up the environmental impact. And there's different metrics that'll be used, like, the amount of energy consumed, the amount of hazardous and non-hazardous waste produced, and then also the amount of greenhouse gases that were emitted as part of the production process of a particular material. And so EPDs are, a nice, useful tool. They're not perfect, right? These are things that we always have to improve. For instance, they're not going to account for the damage to the roadways that I mentioned earlier, right? When a truck has to travel further, and the fact that, that roadway is going to have to be replaced sooner and so on. So they're not perfect, right? They're not going to get everything, but they're the best we've got. And they do provide a very good, tool that you can simply, in a single page, look at and assess and compare, one producer versus another, one material versus another, and so on.
Yeah, and for those of you out there that, if you haven't heard about it already, that are trying to take a look at what producers have and maybe some of these EPDs that are already available, the tool called Embodied Carbon Construction Calculator, EC3 tool, which is a free tool to anybody, is available. And it's found under buildingtransparency.org//EN. So I highly recommend that if people want to investigate this a little bit further, or you can contact me with my email. But unless you have anything else, Zach, I think this has been extremely informative and helpful to not only myself, but I'm sure other people that are available to listen.
It's been my pleasure. Thank you for the opportunity.
Thank you. Have a great day, everybody.